100 miles from land, every safeguard on an offshore platform must work the first time, because there's no backup coming. Out here, harsh weather, limited escape windows, and delayed medical help multiply even small failures into real threats. On shore, you can buy time. At sea, survival is an architecture problem, with redundancy designed into every system. But how deep do those layers go? And what happens when isolation turns ordinary risk into potential catastrophe? This is the architecture of risk, engineered for when help can never arrive fast enough. A single point of failure in offshore power can trigger a chain reaction that puts every life at risk. On a modern platform, electricity is more than convenience. It is the backbone of survival. The chief electrician begins each shift by checking the status of the primary and standby generators. Each is sized to handle 120% of the platform's peak demand, ensuring that if one fails, the other can carry the full load without hesitation. Automatic transfer switches monitor voltage and frequency around the clock. If the primary generator drops out of range, the transfer logic, built with both a microprocessor and a hardware relay, initiates a handover to the standby unit in less than 10 seconds. This two-part fail-safe design means that even if software fails, hardware takes over. For the most critical systems, control room logic, blowout preventers, and fire pumps, a dedicated emergency bus isolates these loads from the rest of the network. In the event of a total blackout, an uninterruptible power supply bridges the gap for up to 5 minutes. This window is designed to hold the line while the black start generator comes online. Quarterly drills test the entire sequence. The chief electrician receives the blackout signal, triggers the black start protocol, and watches as the standby generator spins up. The control room operator tracks voltage restoration. Within 45 seconds, the emergency bus is live. By the 4-minute mark, all essential systems are back online. 5 minutes after the drill begins, the platform's electrical backbone is restored, and the chain of consequence is broken, at least this time. Without this layered backup, even a brief power loss would leave the platform blind and vulnerable, disabling the very sensors and suppression systems that guard against invisible threats. Freshwater is not a luxury offshore. It is a lifeline, engineered with the same rigor as any other survival system. The chief engineer starts every shift by checking the desalination control panel. 2 reverse osmosis trains stand ready, each capable of supplying more water than the crew will ever need under normal conditions. During routine operation, both trains run in parallel but at partial load. If one train fails, for example, a membrane fouls or a pump overheats, the remaining unit automatically ramps up to 150% of its standard output. This surge keeps taps running and cooling systems supplied while the failed train is isolated and repaired. Beneath the deck, stainless steel buffer tanks hold a rolling reserve. Level sensors monitor every gallon, and when the buffer drops to 20%, a high-priority alarm sounds in the control room. It is not just a warning, it is a countdown. At that threshold, the platform has hours, not days, before rationing begins. The chief engineer can manually open an isolation valve to bring a secondary tank online, buying time to fix the problem, or if necessary, prepare for evacuation. Every tank is segregated by double-acting valves, preventing cross-contamination if a single tank is compromised. Life support extends beyond water. The HVAC system, heating, ventilation, and air conditioning, is built with redundant compressors and independent power feeds. If a compressor fails, its twin takes over. Each unit is paired with a variable frequency drive, so a single electrical fault cannot bring down the entire system. Air quality sensors and positive pressure controls maintain breathable air even during a fire or gas event. Without these overlapping safeguards, a simple equipment fault could cascade into an unlivable environment within hours. The system is designed to buy time, not just comfort. Every minute of buffer, every backup, is a margin against the unpredictable. Invisible threats, gas leaks, vapor clouds, and sudden fire are the hazards that offshore safety systems are built to contain. The first line of defense is a dense network of sensors, each tuned to detect hydrocarbons, hydrogen sulfide, or open flame. These sensors are distributed across 4 independent safety zones, with each zone feeding data to its own local controller. When a sensor detects a dangerous concentration, it does not act alone. The system uses a 2 out of 3 voting logic, so at least 2 sensors must agree before the alarm escalates. This reduces false positives, but ensures a real event triggers an immediate response. Once a hazardous reading is confirmed, the safety officer in the control room initiates the emergency shutdown, known as ESD. Within seconds, automated valves isolate the affected process module, and the deluge system comes online. Dual main water lines, powered by independent pumps and cross-connected to prevent backflow, release a curtain of water across the danger zone. Each deluge system is sized to provide at least 30 minutes of continuous coverage, buying time for suppression and evacuation if needed. Mechanical containment is the last barrier. The blowout preventer, called BOP, sits on the wellhead and is equipped with dual stacks of rams, each with independent hydraulics and redundant control valves. If gas is detected at the drill floor, the BOP can close in less than a minute, shearing through drill pipe if necessary. This chain, sensor to shutdown to suppression to mechanical isolation, is designed to stop escalation before it starts. But if any layer fails, as seen in the Deepwater Horizon incident, the consequences can multiply in seconds. Every gap in this sequence is a potential point of no return, underscoring why redundancy is not just a design choice, but a necessity for survival offshore. Evacuation is the final measure when all other defenses have failed. Offshore platforms must provide lifeboat seats for at least 150% of the maximum crew, ensuring space even if a lifeboat is lost or blocked. Lifeboats rest on dual-actuated davits, both hydraulic and electric, so a single malfunction never leaves a craft stranded. Each launch station includes a self-inflating life raft that can be deployed by hand if power fails. The muster process is urgent. At the first alarm, the safety officer checks the roster and starts the clock. Crew gather at assigned muster points, guided by a redundant public address system. If the main digital PA fails, a battery-powered analog backup takes over. Emergency lighting, supplied by both the main grid and a dedicated battery bank, guarantees at least 45 minutes of illumination after blackout. Drills push for a full muster in under 10 minutes. Weather can shut down air evacuation in an instant. Real-time data from satellites and onboard sensors feed a decision tree that determines if helicopters can fly. When the helideck closes, a secondary crew boat waits on a nearby support vessel, ready to evacuate. Every minute lost increases the risk. Redundancy offshore is never just an engineering decision, it's a financial calculation, weighed against the hard numbers that govern every platform. Outfitting a deepwater rig with dual generators, a secondary blowout preventer stack, and surplus lifeboat capacity adds as much as $150 million to the capital budget. That is before factoring in the 12 to 15% increase in yearly operating and maintenance costs, driven by the need for extra spare parts, specialist technicians, and more frequent system testing. But the alternative, accepting a single point of failure, can cost far more. A single day offline can mean $4 to $6 million in lost production, and a major incident can trigger legal claims and cleanup costs that dwarf any upfront savings. Insurers scrutinize redundancy down to the last backup valve. Platforms with fully duplicated blowout preventers and robust evacuation plans can negotiate a 10 to 15% discount on hull and machinery coverage. At the same time, hazard pay for crew, averaging $2,500 a month per worker, reflects the expectation that every person aboard is exposed to a higher baseline risk. even with all these layers in place. Operators run Monte Carlo simulations to model thousands of possible failure scenarios. These analyses show that, when the chance of a catastrophic event exceeds just 0.2% per year, investing in deeper redundancy consistently yields a positive net present value. Every layer of backup is ultimately a bet, one that weighs the cost of prevention against the price of a single bad day. Fatigue is the silent adversary in offshore survival. Crew members average just 5.8 hours of sleep per shift, well below the recommended minimum, while stress levels rise by more than 30% during emergency drills and system tests. In this environment, every backup system ultimately relies on human vigilance to complete the chain of defense. When an alarm sounds, the difference between a swift, coordinated response and a delayed muster can be measured in minutes. Drill records show that fatigue alone can add 2 minutes to a full crew muster, stretching the window of vulnerability. Even the best engineered redundancy cannot compensate for a tired mind or a slow reaction. Data silos further widen the cracks. Safety-critical information remains scattered across separate control systems, making it harder for operators to see the full risk picture in real time. A missed signal or a delayed diagnosis can allow a minor fault to escalate. These are the residual gaps, places where redundancy stops and the human element stands alone. Piper Alpha remains the starkest warning. In 1988, a breakdown in communication during a shift change led to a catastrophic sequence: a single missed permit, a disabled fire suppression system, and a maintenance deferment on a critical pump. Redundant systems that should have contained the fire were offline or bypassed. Within 2 hours, 167 lives were lost. The lesson is clear. No matter how many layers exist on paper, a single lapse driven by fatigue, stress, or incomplete information can unravel the architecture of survival. Offshore, the final barrier is always human. Redundancy buys time, but never certainty. As rigs push deeper and storms grow stronger, even the best engineered layers reveal their limits. Today, every safeguard is a calculated line between routine and disaster. The architecture of risk endures because offshore, resilience is never finished. It is only constantly recalibrated.